Hello students, welcome to the class. So in the last class, we completed few topics of physics. Then let us continue with the next topic. This is in the part 2. So this comes under track 2 of physics, NEET classes. So the next topic is kinetic theory of gases. So in this kinetic theory of gases, it is specially designed, this chapter is for the gaseous properties. It is designed for the gaseous properties here. Means how the gases will exhibit the properties that we will be discussing, right? And there are some special characters which only gaseous molecules will possess. So that is nothing but assumptions of this gaseous kinetic theory. Okay, then next we have the what happens to the pressure, what happens to the volume, then temperature in different condition for the gaseous molecule that we will be discussing. We have gas laws here, and main we will deal with the real gas equation, examples for them. Then we have law of equipartition of energy, and then next degree of freedom. Okay, so many concepts we will be discussing in this chapter. So let us start with the first concept. First, let us see what do you mean by kinetic theory of gases. The kinetic theory of gases, it was developed in the 19th century. It was developed in the 19th century by Maxwell. Okay, so Maxwell, Boltzmann, and many other scientists will give their contribution for the kinetic theory of gases here. Right? The kinetic theory explains the behavior of gases. It explains the behavior of the gases based on the idea that the gas consists of rapidly moving atoms or molecules. It consists of rapidly moving atoms or molecules. Okay. Then in the assumptions, let us see the properties of the gaseous molecules. See here, that is assumptions of kinetic theory of gases. Every gas consists of extremely small particles which are known as molecules. So what do you mean by molecules here? We study in chemistry, what do you mean by atom? What do you mean by molecule? Right? So here, what is this molecule? A gas consists of extremely small particles. Those particles are called as what? Molecules in case of kinetic theory of gases. Okay, so in chemistry, we define molecules in different way. But here we are seeing based on the gaseous properties. Then next, the molecule of a given gas are all identical but are different from those of another gas. Here we say that the molecules of given gas are all identical. They are all identical, but they are of different. They are different from those of another gas. They are different from those of another gases here, right? Then next, the molecules of a gas are identical, spherical, rigid, and perfectly elastic point masses. Here we say that the gaseous molecules, they are spherical, they are rigid, and they have the perfectly elastic point mass. It is having the perfectly elastic point mass here. Then next, the molecular size is negligible. So we say that in gaseous properties, when we are studying, we say that these gaseous molecules are having the negligible size in comparison to intermolecular distances, in comparison to the intermolecular distance here, that is given by to the power of 10 raised to minus 9 meter, to the power of 10 raised to minus 9 meters here. Okay, the speed of gas molecules lies between, the speed of gas molecule, it lies between 0 and infinity. The speed of gas molecule, it lies between 0 and infinity, which means that it must be very slow or it must be sometimes very high. That is nothing but what? The gaseous molecules lie between 0 and infinity. The next point is the distance covered by the molecule between two successive collision is known as, here the distance between, the distance covered by the molecule. Here what happens, we know that the gaseous molecules are moving randomly. When they are moving randomly, here what happens? That is, between two successive collisions, it is known as free path. Whatever the distance it covers, that is called as free path, and the mean of all free path is known as what? Mean free path. Here what they say, the molecules are moving in a random path. When they are moving in a random path between two successive collision, whatever the distance it covers, that is called as free path. And the mean of all these molecules free path, we take it as what? Mean free path. We take it as mean free path. Okay. The next, the number of collision per unit volume in a gas, it remains constant. We say that the number of collisions per unit volume in a given gas, it remains constant. Okay. For a given volume of gas, the number of collisions will be fixed. It will not change here. Then next, no attraction or repulsion force acts between the gas molecules. Okay, so here in between the gas molecules, there is no attraction or repulsive force. They are simply randomly moving in the given container. Okay. It is not that one molecule will attract the other molecule and the few molecules will repel the other molecule. It is not that. Here all the gaseous molecules are moving randomly and they don't have any attraction or repulsion force between them. Okay. The gravitational to extremely attraction among the molecules is ineffective due to small masses and very high speed of molecules. Here the molecules are moving randomly with very high speed. They are moving with very high speed. And here whatever the masses are there, it is very negligible. The mass of a given gas is very negligible. Therefore, what happens? Whatever the, what you can say, whatever the gaseous molecules are there, the gravitational force will not act on them. The gravitational force will not act on the given mass of a gas. Okay. Then next. Gas laws. So gas laws here. What are the different gas laws? Let us discuss. So here the gas laws, based on the gaseous properties, the gas laws were developed. That is given by assuming permanent gases to be identical. Through experiments, it was established that gases, irrespective of their nature, obey the following laws. Here we say that the gaseous molecules will obey the following laws here. So what are the laws here? That is Boyle's law at constant temperature. First law is Boyle's law. The statement for Boyle's law is, at constant temperature, the volume of given mass of a gas is inversely proportional to its pressure. We say that is at constant temperature, the volume of a given mass of a gas is inversely proportional to its pressure. Here the equation is given. You can see the equation. That is V is inversely proportional to 1 divided by P. V is inversely proportional to 1 divided by P. That implies PV is equal to constant. That implies PV is equal to constant here. Right. Then for a given mass of a gas, the equation can be written as P1V1 is equal to P2V2. For a given gas, the equation is given as P1V1 is equal to P2V2, right? So this is what? This is Boyle's law. So remember the Boyle's law so that the next law will be clearly understood. Boyle's law defines at constant temperature. We define that at constant temperature, the volume of a given mass of a gas is inversely proportional to the pressure. That is PV is equal to constant, or it can be written as P1V1 is equal to P2V2. Then next we have Charles' law. What is this Charles' law statement? Charles' law states that at constant pressure, the volume of a given mass of a gas, it is directly proportional. The volume of a given mass of a gas, it is directly proportional to absolute temperature. Okay, so here they say that the volume is directly proportional to temperature. The Charles law specifies at constant, what we can say, at constant temperature, sorry, at constant pressure here. This is for constant pressure, right? Then next, that is V is directly proportional to T. V is directly proportional to T. Then next, the same equation can be written as V by T is equal to constant. It is V by T is equal to constant. So for a given gas, V1 by T1 is equal to V2 by T2. So in case of Boyle's law, how we write? V1 is equal to P2 V2. Similarly for Charles law, we write it as V1 by T1 is equal to V2 by T2, right? At constant pressure, the volume of a given mass of a gas increases or decreases by 1 upon 273.15 of its volume at 0 degree Celsius, at 0 degree Celsius for each 1 degree rise or fall in the temperature. For each 1 degree Celsius rise or fall in the temperature. So volume of the gas at T degree Celsius is given by, volume of the gas at T degree Celsius is given by, it is Vt is equal to V naught into bracket 1 plus T divided by 273.15. So where V naught is the volume of gas at 0 degree Celsius. So we say that V naught is what? It is the volume at 0 degree Celsius. Okay, this is what the Charles law. So Boyle's law is at constant temperature. Charles law is at constant pressure. So after this, we have Gay-Lussac's law, or it is also called as Reynolds law. Okay, so what is the statement here? At constant volume, the pressure P of a given mass of a gas, it is directly proportional to absolute temperature, directly proportional to absolute temperature. Okay, see here, that is given by V by T, sorry, it should be P by T, that is P by T is equal to constant. Therefore the equation can be written as P1 by T1 is equal to P2 by T2. Then next we have at constant volume, the pressure P of a given mass of a gas increases or decreases by 1 upon 273.15 of its pressure at 0 degree Celsius for each 1 degree Celsius rise or fall in the temperature. Okay. Then next we have volume of the gas at T degree Celsius. It is given by that is Pt is equal to P naught into bracket T1 1 plus T divided by 273.15, where P naught is the pressure of a gas at 0 degree Celsius, right? So this is what Gay-Lussac's or Reynolds law, right? Then next we have Avogadro's law. Avogadro's law, it states that equal volume of all the gases under similar conditions of temperature and pressure, it contains equal number of molecules. It consists of equal number of molecules here, right? Under similar conditions of temperature and pressure, it contains equal number molecules. This statement is called Avogadro's hypothesis. This is called as what? Avogadro's hypothesis. That is, volume of the gas under similar conditions of temperature and pressure, it contains equal number of molecules. So according to Avogadro's law, we can write it as Avogadro's number, the number of molecules which is present in. What do you mean by Avogadro number? So in chemistry, you might have studied this. Avogadro number is nothing but it is the number of molecules present in 1 gram mole of a given gas, it is called as Avogadro number. Okay, the Avogadro number, the value is constant and the value is 6.023 into 10 raised to 23 per gram mole. 6.2023 into 10 raised to 23 per gram mole. Okay, at STP, at standard temperature and pressure, or NTP, that is temperature is 273 Kelvin and pressure is 1 atmosphere and volume is 22.4 liter of each gas has 6.023 into 10 to the power of 23 molecules. Means here 1 atmosphere at standard temperature and pressure, the gaseous molecules consist of, these many, that is Avogadro number here. Okay, 1 mole of any gas at STP occupies 22.4 liter of volume. So this is regarding the Avogadro's law. Then next, standard or perfect gas equation. What do you mean by standard or perfect gas equation? That is gases which obey all the gas laws in all conditions of pressure and temperature are called as what? Perfect gas. So what do you mean by perfect gas or standard gas? It means that gases which obey all the gas laws in all conditions of pressure and temperature, these are called as what? Perfect gases. So equation of perfect gas is given by is PV is equal to nRT. It is given by PV is equal to nRT, where P is pressure, V is volume, T is absolute temperature, and R is universal gas constant, where N is the number of moles of a gas. Okay, the universal gas constant, the value of R is found to be 8.31 joules per kg per Kelvin. This is the word joules per mole per Kelvin. This is the value of the universal gas constant. Then next we have the real gases. What do you mean by real gases here? Real gases deviate slightly from ideal gas laws because real gas molecules attract one another. Here ideal gases, they will not attract one another, but the real gases will attract one another. Real gas molecules occupy a finite volume. They occupy finite value, and real gases are negligible volume. Right. Then next we have van der Waals gas equation. So van der Waals gas equation is given by, it is P plus A divided by V square, and in another root we have V minus B, which is equal to R into T, where A and B are constants, here. Then the pressure due to ideal gas equation. Is given by P is equal to 1 divided by 3 mn divided by V. Okay, see here. That is A and B are called as van der Waals constant, and the pressure due to an ideal gas is given by P is equal to 1 by 3 mn by V. Here we can also write it as C2 is equal to 1 by 3 rho C square. This is what in terms of density. For 1 mole of an ideal gas, it is given by P is equal to 1 by 3 m by V C square, where m is the mass, n is number of moles, and V is the volume of the gas. Here C is, it is nothing but it is C1 square plus C2 square plus C3 square, so on up to Cn square by n. Okay, this is nothing but root mean square velocity. It is given by root mean square velocity of a given mass of a gas. Capital M is the molecular weight, and rho is the, P is the pressure, and E is the energy per volume. Then we can also write the expression for pressure of a gas as 2 by 3 into E. E is energy, 2 by 3 is constant. So here we can see that the pressure of a gas is directly proportional to energy. So see here, we have some conclusions based on kinetic energy of a gas, that is given by kinetic energy, kinetic energy of translation per molecule of a gas is given by, per molecule of a gas is given by E is equal to 3/2 into kT, where K is Boltzmann's constant. So average kinetic energy of translational per mole of a gas is given by. So the average kinetic energy is given by 3/2 into RT, where R is universal gas constant. We already know the value here, 8.31 joules per mole per Kelvin. Okay, for a given mass of a gas, the kinetic energy is directly proportional to what? Temperature. This is very important assumption, that kinetic energy is directly proportional to temperature here. Okay, means as the temperature increases, means the kinetic energy of the molecule also increases. Okay. Then next we have, it is also given by T1 by T2. So root mean square velocity of the gas molecules is given by, for a given gas, it is C is directly proportional to root of T, means velocity is directly proportional to square root of temperature. Then for different gases, C is proportional to 1 upon root m. It is directly proportional to 1 upon root m here, which means that is m is what? Molecular weight. So the relation between velocity and weight, it is given here. Then for Boltzmann constant, K is equal to, it can be written as R divided by N, where R is an ideal gas constant. Okay, we know that N is the Avogadro number. The value of Boltzmann constant is given by 1.38 into 10 to the power of minus 28 joules per Kelvin. The average speed of molecules of a gas is given by, the average speed is given by what? It is V1 plus V2 plus so on up to Vn divided by divided by N. Right. Then next we have the degree of freedom. So what do you mean by degree of freedom? Very important concept. Degree of freedom is nothing but, it is, you're specifying the position of the molecule with the help of degree of freedom. So the degree of freedom for a dynamic system is the number of directions. It is the number of directions in which it can move freely. Or the number of coordinates required to describe completely the position and configuration of the system. So here we can specify the degree of freedom for specifying the position and configuration of the system, and it is denoted by N. It is denoted by capital N. Then next, degree of freedom of a system is given by N is equal to 3A minus R. So sometimes we take it as 3K minus R also. Okay, where A is the number of particles, then R is the number of independent relations. So we write it as 3N minus K, where K is the number of independent relation. For example, if monoatomic is there, monoatomic means single atom. That time here what happens? It is not bonded with any other atom here. Therefore, the number of independent relation will be 0 in case of monoatomic. Such a way, diatomic, there will be one bonding between the two atoms. So that is number of independent relation will be 1. So like that we can define the number of independent relation for degree of freedom. Then next, degree of freedom for monoatomic gas. So for monoatomic gas, the number of degree of freedom after calculation here it becomes, because A value will be 1, and as I told you, the value of R will be 0 in case of monoatomic. Therefore, it becomes 3 into 1 minus 0, that is 3. Then for diatomic, so diatomic, what happens here? For diatomic, the value is in the formula. So here this is the formula, 3A minus R. A value, if you take it as 2, because diatomic here, okay, therefore it becomes 3 2s are 6 minus 1 relation, therefore 6 minus 1 is 5. Then for non-linear triatomic gas, it is given by 6. Then for linear triatomic gas, it is given by 7. Okay, non-linear, linear in the sense in a single line, the 3 molecules are arranged. Non-linear in the sense they are not arranged in a same line. Okay, that is called as what? Non-linear triatomic gas. Next. specific heat of a gas at constant volume, it is given by. So here we have specific heat capacity at constant volume. The relation is given for what? Degree of freedom. Okay, that is given by F by 2 into R. It is given by F by 2 into R. Then for specific heat capacity at constant pressure, it is given by Cp is equal to F by 2 plus 1 into R. Then third one is ratio of specific heat of a gas at constant pressure and volume is given by gamma is equal to 1 plus 2 divided by F. So these all three formulas are important. The specific heat capacity at constant volume, specific heat capacity at constant pressure, and for constant volume and pressure, it is given by gamma is equal to 1 plus 2 by F. Okay. Then next we have the mean free path. What do you mean by mean free path here? The average distance traveled. The average distance traveled by a molecule between two successive collision is called as what? Mean free path. It is called as mean free path and it is denoted by gamma. The mean free path value is given by k into t divided by root 2 into pi sigma square into t. K is Boltzmann constant. Then T is absolute temperature, phi is constant, 2 is constant, sigma is diameter of the molecule, and P is the pressure of the gas. So diameter of the molecule, pressure of the gas, temperature, and Boltzmann constant. The mean free path is given by lambda is equal to, lambda is proportional to T. That is, mean free path is proportional to temperature. And it is inversely proportional to what? It is inversely proportional to pressure. This we need to remember here. Okay. Then the next concept we have, that is Brownian motion. What do you mean by Brownian motion here? The continuous random motion of the particles of microscopic size, which is suspended in air or any liquid is called as what? Brownian motion, or it is called as Brownian of microscopic motion. Means the continuous random motion. All we know that the molecules are moving continuously in a random motion. Okay. So such a motion under microscopic size suspended in air or any liquid is called as what? Brownian of microscopic motion. Then Brownian suspended motion in both is observed with many liquids and gases. Brownian motion is due to the unequal bombardment of the suspended particles by the molecules of the surrounding medium. What is the meaning of this? That is, here, why this Brownian motion occurs here? Because of the unequal bombardment of the suspended particles by the molecules of the surrounding medium. Then next, law of equipartition of energy. So what do you mean by law of equipartition of energy? It states that the energy of each degree of freedom is given by, means here the energy is equally distributed. The energy is equally distributed among all the molecules, and it is given by, E is equal to 3 by 2 N into Kb into T. This leads to a relation that is PV is equal to 2 by 3 into E. This leads to a relation of PV is equal to 2 by 3 into E. So if P is pressure of a gas, V is volume, T is its temperature, then rho is the density. Then PV is equal to constant at constant temperature. Then P by rho is called as what? Constant at constant temperature. And another form, this is what? Another form of Boyle's law. So already Boyle's law we define in terms of constant temperature, in terms of pressure and volume. Here the Boyle's law in terms of density also we are defining, that is P by rho is equal to constant. Okay, then P by T is equal to constant. This is Charles' law. Then another equation for Charles' law, we can also write it as V by T is also equal to constant. Okay. Then the relation between specific heat capacity at constant pressure and specific heat capacity at constant volume is given by Cp minus Cv is equal to R, where R is called as universal constant. Universal gas constant. So this relation is also called as Mayer's relation. This relation is also called as what? Mayer's relation here. Okay, students. Then next we have the pressure exerted by a gas. The pressure exerted by the gas containing vessel due to continuous collision of the molecules against the wall is given by PV is equal to 1 by 3 Nm V square RMS. V square RMS. So V RMS is what? Root mean square velocity. It is 1 by 3 N into M. That is also given by P is equal to 1 by 3 M by V square, VRMS square. Okay. Then 1 by 3 mass per unit volume is called as what? Density. It is 1 by 3 rho into VRMS square. Then the relation between pressure and kinetic energy is given by, so pressure is equal to 1 by 3 N into M by V into VRMS square into VRMS square. Here, the value of 1 by 2 M VRMS square can also be written as 3 by 2 into P into V. But we already know that 1 by 3 1 by 2 it should be. 1 by 2 M VRMS square is nothing but what? Average kinetic energy of a gas molecule. Therefore, the kinetic energy is given by N into bracket 1 by 2 M VRMS square. That is for N number of particles. And it is also given by 3 by 2 into PV. 3 by 2 into PV. Right? Then next. Kinetic energy per unit volume of the gas E is equal to, that is 3 by 2 into PV. Then next we have, just now we defined many times, root mean square. What do you mean by this root mean square velocity? Let us see. The root mean square velocity is derived by using the equation of pressure for a given mass of a gas. That is P is equal to 1 by 3 M by V into root mean square. Therefore, we can simplify this equation for what? V square, root mean square value, that is equal to. So transfer the terms, you will get it as 3 into P into V divided by M. M is what? Mass of gas. So VRMS is equal to root of 3 PV divided by M. So VRMS is equal to root of 3 PV divided by M, and that is equal to root of 3P divided by rho. That is mass per unit volume density. So that is equal to, in terms of universal constant and temperature, we can also write it as root of 3 RT divided by M. And that is equal to root of 3 KT divided by M, since R is equal to Avogadro number into K. Okay, so this is what the root mean square velocity expression in terms of density, in terms of molecular weight, in terms of Boltzmann constant. So based on the given data, we can use the equation and calculate the root mean square velocity. Then next we have the different types of speeds of gas molecules. The most probable speed is given by. So the most probable speed is what? It is the speed which maximum number of molecules in a gas have at constant temperature, and is given by, and it is given by V most probable speed is equal to, that is root of 2 RT divided by M, and that is equal to root of 2 by 3 VRMS. 2 by 3 VRMS, that is equal to 0.816 VRMS. 0.816 VRMS. Okay. So the most probable speed is equal to, it is 0.816 VRMS. Then the average speed is given by, it is the arithmetic mean of the speed of molecules in a gas at a given temperature. So the root mean speed of a molecule is given as V average is equal to V1 plus V2 plus V3 so on up to Vn divided by N. According to the kinetic theory of gases, it is given by root of 8 RT divided by pi into M, which is equal to root of 8 divided by 3 pi root of VRMS. which is equal to 0.92 VRMS. That is equal to 0.92 VRMS. So here the relation between VRMS, that is root mean square, and the average velocity and the most probable velocity is given by, it is given by VRMS is greater than V average, and that is greater than most probable speed. So already we defined the degree of freedom. So just some definition to recall the value of specific heat constant and constant volume and temperature, pressure, that is Cp and Cv. See, it is the quantity of heat required to raise the temperature of unit mass of a gas to 1 degree Celsius or 1 Kelvin at constant volume. So molar specific heat at constant volume is given by Cv. The amount of heat required to raise the temperature of 1 mole of gas through 1 Kelvin at constant volume is given by Cv. Okay. If mW is the molecular weight of the gas in gram, then Cv is equal to mW into Cv. See here, at constant volume, there is no external work is done by the gas, and total heat given to it is utilized for increase in internal energy. So we write it as du is equal to mu into Cv into dt. The next, specific heat capacity at constant pressure. It is given by, it is the quantity of heat required to raise the temperature of 1 gram of gas through 1 degree Celsius at constant pressure. So we have same definition for both. Only the thing is, one we define in terms of constant volume, one we define in terms of constant pressure. Then next. So for molar specific heat constant at pressure is given by what? This is what? To raise 1 gram of mole of gas through 1 Kelvin. Here, whatever the amount of heat is required. Here, in case of specific, we define it as for 1 kg. In case of molar, we define it as 1 gram mole. If mW is the molecular weight of the gas in gram, then Cp is equal to mW into Cp. Then according to Mayer's relation, already we have discussed, Cp minus Cv is equal to R. Then the relation between Cv, Cp and gamma for ideal gas is given by Cv is equal to F by 2 into R, and Cp is equal to F plus 2 divided by 2 into R. Here gamma is equal to, it is Cp by Cv, that is adiabatic constant. That is called as what? Adiabatic constant here. Okay. Then next, the value of Cp, Cv and gamma for monatomic, diatomic and polyatomic. See the values, we should remember this to solve the numerical. It is very, very important. Then for monatomic, the value of Cv is given by 3 by 2 into R. The value of Cp is given by 5 by 2 into R. And the value of gamma is given by 1.67. Why? Because the Cp-Cv ratio is gamma. That is adiabatic constant. So if you take the ratio, you will get it as 1.67. Then for diatomic, it is given by 1.4, the gamma value, and Cv value is 5 by 2 into R. Then Cp value is 7 by 2 into R. Then for polyatomic, Cv is 3R, Cp is 4R, and gamma value is 1.33. Gamma value is 1.33. Okay. Then thermodynamic parameters for a mixture of gases. For a mixture of gases, that is given by equivalent molar mass is equal to, it is given by m is equal to mu1 m1 plus mu2 m2 divided by mu1 plus mu2. So when mu1 moles of a gas with molar mass m1 are mixed with mu2 moles of a gas with molar mass m2, the equivalent molar mass of the mixture is given by, the equivalent molar mass is given by m is equal to mu1 m1 plus mu2 m2 divided by mu1 plus mu2. Okay. Then next, internal energy of the mixture. The internal energy of the mixture is given by the total energy of the mixture is equal to u1 plus u2. Then CV is what? That is specific heat capacity at constant volume. For that, the expression is given by equivalent molar mass expression is given by mu1 CV1 plus mu2 CV2 divided by mu1 mu2. Similarly, for Cp, it is given by mu1 Cp1 plus mu2 Cp2 divided by mu1 plus mu2. Then gamma is equal to, so it is the ratio of Cp by Cv, Cp by Cv. So solve the equation for Cp by Cv. After all the simplification, see what we are getting there. It is mu1 plus mu2 divided by gamma mix minus 1, and that can be also written as, that is mu1 by gamma 1 minus 1 plus mu2 by gamma 2 minus 1. If two identical gases at temperature T1 and T2 are mixed, there is no loss of energy. Then the temperature of the mixture is given by T1 N1 plus N2 T2 divided by N1 plus N2 divided by N1 plus N2 is the equation when the temperature is T1 T2 are mixed. Then already we have discussed about van der Waals equation. So the van der Waals equation is given by what? For 1 gram, the equation becomes P plus 1 V A by V square into bracket V minus B. So here PB are constant, van der Waals constant. Sorry, AB are van der Waals constant. PV are pressure and volume, and V square is what? Volume here. That is equal to R into D. Then for mu gram of mole, it is given by P plus mu square Q by V square into bracket V minus mu B is equal to mu RT. So in the first equation, it is for 1 gram of mole. Second equation, it is for mu gram. This is called as van der Waals equation. Then the real gases obey this equation to a sufficient extent at high pressure and low temperature. Yes. So this completes the synopsis of kinetic energy of gases, kinetic theory of gases. So in the next class, we will continue with the multiple choice questions. Okay, students, thank you.